Okay, AP Calculus, we're looking at 2015 problem number one. This is a very, very commonly designed problem. Again, you're not going to see problems that this one's about drain pipe, but you're going to see problems where it's, things that are entering and then things that are leaving, okay? So people could be entering into a line and exiting in line. Could be putting gravel onto a pile and taking gravel off of a pile. So the idea is that things are being gathered and then things are departing is kind of what's happening. This situation is a drain pipe. It's partially clogged, but you have water that's entering the drain pipe at a certain rate, R of T, and it's leaving at a certain rate, D of T. And we're going from T0 to 8 during that time frame, okay? And that's in hours. And then we're measuring the volume in cubic feet. There's 30 cubic feet of water in the drain pipe at time is equal to 0. Question A says how many cubic feet of rainwater flow into the pipe during the 8-hour time interval? So how many cubic feet flow in? So we're just looking for the amount in. We're not looking for any amount out. So the amount in. So you'll gather that accumulation through an integral. So the integral of R of t dt, 0 to 8. So just writing that down will get you a point. This is a calculator problem. Can't do it without the calculator, really. I go in there, and I've got this function 20 sine of t squared, so x squared divided by 35. And I'm going to make sure that I am working in, let's see, mode. I'm going to be in radians. I don't want to be in degrees. And then I notice I have that 20. So I know that my window, I know that my y values are going to have to go up to negative 25 bottom or positive 25. So I can at least, see some of the graph. So here goes the graph. This is my sine graph. And it says how many cubic feet from 0 to 8. So it's accumulating. So I'm going to gather that under number 7, 0 to 8. And as I collect all that, I get that 76.570. 76.570 cubic feet. There you have it. So get some points by just doing that. Problem B is the amount of water in the pipe increasing or decreasing at time 3. So the amount of water in. So think about it. If we have, like, say, I don't know, water coming in at a rate of 10 cubic feet per minute and it's leaving at 8 cubic feet per minute, well, then we would say that the amount of water is increasing. If the amount of water coming in is, say, coming in at a rate of, say, 6 and it's leaving at a rate of 8, well, then we would say that the amount of water in the pipe is decreased because it's leaving faster than it's coming in. So we're going to compare R of 3 and D of 3. So we're going to find the rate at which it's entering. And so I currently have that typed in here. So I'm going to second calculate number 1 to find that value. I'm going to type in 3. And so I have R of 3 is equal to 5.086. And then we're going to check D of 3. And I'm going to type in Y sub 2 here for my D of 3. And it is negative 0.04 x cubed plus 0.4 x squared plus 0.96x. And there I have it. And so I'm going to, we'll go to the table on this one. I can look at y sub 2. So if you type in 3, you see my first one is 5.086. Next one is 5.4. 5.4. So D of 3 is equal to 5.4. So water is leaving at a rate greater than it is arriving. Therefore, the amount of water in the pipe at time equal to 3 hours is decreasing. Okay, and all that's really good stuff. In fact, there's two parts to that. Number one, you want to consider the R of 3 and the D of 3, so they'll give you a point for that. And then justifying your answer is really important. Okay, so again, this is kind of a stuff that's gathering and then leaving. We're going to do a couple problems like this. Problem C says, at what time is the amount of water piped at a minimum? Minimum. Well, you remember that minimums occur when the derivative f prime changes from negative to positive. Okay? All right? So we can look at the derivative of this thing, but first let's look at the amount. The amount of water in the pipe is going to be equal to the start plus the displacement. So that's equal to, the start is 30. We start with 30, and we add on to that, the amount that's arrived and the amount that's left. So the amount that's arrived is the integral from 0 to whatever time, okay, of r of t dt. So that will tell you how much is gathered, okay? And then we are going to subtract the amount that's gone. So that's 0 to t of d of t dt, okay? So that's the amount of water, okay? That's the amount of water at any time. So we're going to do a couple things here. Let's check how much is at the beginning. Time equals 0, there is 30. We know that. Let's check time is equal to 8. So that's the end point. Let's see how much time there is, or how much water there is at 8. So if I want to check how much water there is at 8, I've got to type this integral in. Notice what I've got. I've got this r of t minus d of t. So that's y1 minus y2. So I'm going to save some time here, and I'm going to go down here. I'm going to go into my vars, y vars, function, y1, minus vars, y vars, function, y2. And I'm going to take off my first two. So now I have y1 minus y2. So I'm going to calculate number 7 to figure out what that integral is. So you can use one integral instead of two. I wrote it using 2. But we're going to calculate that from 0 to 8 right now. 0 and 8. And I get 18.54. So 30 plus 18.54, 3, which is equal to 48.543. Okay? Now, so that's the endpoints, but you need to check then. It says, when is it at a minimum? Well, that's when the derivative changes from negative to positive. So let's look at the derivative of this guy. We're going to take the derivative of that. The derivative of 30 is 0. Okay? The derivative of an integral, you're just left with r of t. The derivative of this, you're just left with d of t. Okay? So we're going to look at r of t minus d of t. And that is this guy right here, y1 minus y2, r of t minus d of t. Let's look back at that graph. Well, I'm going to change it just for a second. I'll just enter a subtraction sign again. We can look at the graph. And let's look if it ever changes from negative to positive. And I'm going to argue that it changes from negative to positive right there. If I change my window a little bit and I put my y minimum at negative 8, my y max at positive 6, and now I graph that. Let's see if we can see a little bit better here. Comes up. So it's positive, and then it's negative, positive. So again, we said that a minimum occurs when the derivative goes from negative to positive. So I'm going to calculate a 0 to find where that happens. And if I calculate that 0, I go enter left, enter right, enter on guess, and I get 3.271 time equals 3.271. So I got to check time equals 3.271. So I'm going to go to calculate number 7, and lower limit is 0, upper limit is 3.271, and it's going to see how much I get. I get negative 2.03. So 30 minus 2.035. And if we try that, 30 minus 2.035, we get 27.965. So notice all those three things that we had to check, and this is the correct one. The answer is, that the amount of water in the pipe is at a minimum at time equals 3.271, and the amount is 27.965 cubic feet. And there you have it. Okay. I'm going to scoop my stuff down here so you guys can see better. Sorry about that. We're at 12 minutes right now, so I got to get going here. I know that's challenging, you guys, okay? But just understand that out of 9 points for each question, the average across the nation is like 3. So there's parts you could get up here, okay? Question D says, the pipe can hold 50 cubic feet of water before overflowing. So at max 50, okay? At maximum 50, then it's going to fall apart, okay? For time greater than 8, water continues to flow into and out of the pipe at the given rates until the pipe begins to overflow, right? But do not solve an equation involving one or more integrals that gives a time W when the pipe will begin to overflow. Well, we're wondering when the amount is equal to 50. When is the amount equal to 50? Well, the amount is 30 plus the integral of R of t dt minus the integral of d of t dt. Okay? We're wondering when that's equal to 50. Now, what are our bounds? We start at 0. We don't actually know the time. We don't know the specific time. But it says time will be W. So that will tell us at what time, if we solve that, that will tell us exactly the time that it's equal to 50 and it starts to overflow. This is not an easy problem, okay? But there's a little bit of information for you about how to do it. We're going to do a couple more because this is one of the most commonly asked type of problems. And so I want to make sure that you get the idea of things entering and things leaving. Not an easy one to start with, but we'll try to make it clear and make more sense as we move along.